In this last section of Chapter 8, in 8.5, we're going to talk about what are called critical paths and the critical path algorithm. So, the idea of this is to start sooner rather than later. In other words, the greater the total amount of work that lies ahead of the task, the sooner that task should be started. In fact, that was one of the problems that we saw with our decreasing time algorithm in 8.4. In order to introduce this idea, we're going to introduce the concepts of what are called critical paths and critical times. So for the critical path, for any given vertex x of a project diagram, the critical path for x is the path from x to the end with the longest processing time. When we add together the processing times of all the tasks along a critical path for any particular vertex, we get the critical time for x. And then the path with the longest processing time from start to end is going to be called the critical path for the project. And the total processing time for that path is going to be called the critical time for the project. So once again, we have a diagram here that shows us building that Martian habitat unit that we've been talking about, and we're going to find some critical paths. So let's go ahead and start by looking at this critical path for the vertex HU. So for HU, there are basically three different paths that you can consider. And really what you want to think about is, how long would it take to get from HU to the end? Well, if we go down this bottom path, 4 plus 2 is going to be a time of 6. So there would be your critical time for that path. For the one in the middle, 4 plus 3 would give you a finishing time of 7. And for this path on top, you would have 4 plus 1 is 5, plus 6 is 11. Now, whichever one is longest is your critical path. So that would be the 11, which would be going from HU to IC1 to FW6 to the end. And that would have, again, a total time of 11. So again, there's that math that we just talked about. So the critical path, again, is going to be the one that goes HU to IC to FW to the end. That critical path is going to be 11 hours. I'm not sure what the circles, I think they ended up kind of in the wrong spots, but again, that path is from here up to here, over to here, and back to the end. Okay, so next, let's go ahead and do the same thing for this vertex AD. There's really only one path from AD to the end, which is to go from AD to ID to PU to EU all the way to the end. And when you add those together, you end up with a total critical time of 18 hours. And again, that's just because there was no other path to go. It was not as if any of these ever went up to any of the other paths. It only went through that bottom path, so AD8 only has one possible critical time. So to find the critical path for the entire project, we need to find the path from start to end with our longest processing time. Let's just try to eyeball where that would be. So looking at the largest numbers, lots of numbers here in the middle. 7, 4, 4 is probably more than the rest. Let's see, 7 and 5, that's going to add up to be more than the rest of these. And then IC and FW, definitely more than PD and EU. So it looks like that might be our critical path. It would be to go through these two vertices, through these three, up through these two, and back to the end. And in fact, that is it. So if you are seeing that along with me, nice job. That would be our critical path. And when you add those together, you'll find that the critical building time for our project is 34 hours. So obviously that works out somewhat well in that small digraph, but when we get to bigger digraphs, we're going to need some different ways to do it. And it might not be possible to just eyeball the answer like we did in that previous problem. The good news is we're going to have this algorithm, which is called the backflow algorithm, which we can use to help us find critical paths. So here's what the backflow algorithm says. Step 1, find your critical time for each vertex of your diagram. So this is done by basically starting at the end and working your way backwards towards the start. And so basically what you'll do is you'll keep finding critical times for every single path all the way till you get back to the very beginning. What we will do for notation is we will use these square brackets instead of the parentheses to distinguish the critical time from the processing time. So we've got a diagram of what that looks like. It'll probably make a little bit more sense though once we work through an example. Now step 2, once we have the critical time for every vertex, the critical paths are found by just following the path along our largest critical times. In other words, the critical path for any vertex is obtained by starting at X and moving to the adjacent vertex with the largest critical time. And from there to the adjacent vertex with the largest critical time, and so on. So let's use backflow algorithm to find each of the critical times for our Martian habitat unit diagram. Zoom in a little bit here. So obviously, starting at the end, each of these different tasks, FW, PD, and EU, are each going to have a critical time which is the same as what it would take to process them in the first place because they don't have anything in front of them. Now IC has to go through FW6, that is the largest, so take 1 plus 6 tells you that IC has a critical time of 7. Now we already found HU4. Looking at each of these, it was the largest, 7, 3, and 2. Obviously 7 is the biggest, so we already knew that HU4 had a processing or a critical time of 11. Now for PU3, that one should also be pretty easy. There's only one that it could go to, which is EU, which has a critical time of 2. So take 2 plus 3 is 5, and there would be your critical time for PU. Next, let's jump up to PL. PL can only go to one place, which is IC. The critical time there is 7, plus our processing time is 4, and 7 plus 4 is 11. So notice that you're adding together the number in the parentheses with the number in the brackets for the one that comes after it. So don't try to add the two parentheses together. Make sure to add what's in the parentheses for the one furthest left with the brackets for the one on the right. So for IP4, as we're looking there, we have two options. IP4 can either go to PU3, which is 5, or HU4, which is 11. We're always going to pick the one which is largest, so in this case, the 11. So 11 plus 4 gives us a critical time of 15 for IP4. Okay, next let's look at ID5. That can only come from go to one thing, which is PU, which does have a critical time of 5. So take your 5 plus 5 gives you a critical time of 10. Next, let's look at IW7. That can either go to IP, which is 15, or ID, which is 10. Again, picking whichever one is largest, that's going to be the 15. So take 15 plus your processing time of 7 is going to give you a critical time of 22. Let's keep working our way from right to left. So for IF5, we have two options. We either have the 11 or the 22. Obviously, the one which is largest is the 22. So take 22 plus 5. Tells you your critical time for IF is 27. Okay, so now let's go ahead and go from top to bottom. For AP7, obviously there's only one that it can go to, which is this IF5, which has a critical time of 27. So take 27 plus 7 is 34. Do the same thing with AF, since it could only go to IF as well. So 27 plus 5 is 32. For AW6, that can only go to IW7, which has a critical time of 22. So take 22 plus 6 is 28. And finally, for AD8, only one place it can go is ID5, which has a critical time of 10. So take 10 plus 8 is 18. So again, these next couple of slides will talk us through that. And you can see once we get to this slide, right, let's see, keep going, almost there. Okay, right here, now we have all those same numbers that we had in our brackets on this slide as well. So again, those previous slides just going to talk you through step by step what I showed you. So feel free to go back and look at those if you'd like to. So the critical path is going to be the one that always goes through the longest time. So starting at your start, that would have to go up to AP where the critical time is 34. From there, you have to go to IF with a critical time of 27. Now you have two options, 11 or 22. Remember, critical path is always going to be the longest, so that's going to be 22. From there, you only have one option, which is to go to IP. From there, you've got two options, either HU or PU. HU is 11, PU is 5, so that would be HU as our critical path. And then from there, one last choice to make, which is between IC, which has 7, PD is 3, EU is 2. So 7 wins that battle, and we move on to the end. So there would be our critical path that we found using our backflow algorithm. All right. So when we want to get to the actual scheduling of this, we're going to need to create a critical path priority list. And when we do that using the critical path algorithm, that's going to be kind of how we make our schedule. So what we're going to do is we're going to, step number one, and this would be a good slide to make sure you copy down, but to use the backflow algorithm to find all of the critical times for every task in your project. So there's your step one. That's basically what we just did. Step number two is you're going to create your priority list using the critical times that you get in step one. You're going to create your priority list so that the tasks are listed in decreasing order for their critical times. In fact, they've got a list of those right here. So again, listing out those tasks, AP had the largest critical time of 34, then would be AF at 32, then would actually be AW with 28, then IF with 27, and so on and so forth. You can see the critical times in the brackets decrease on each of these, and so you're listing those out for this priority list. From there, once you've built the priority list, step number three is you create your schedule. Again, that's the same as you would with any other priority list. Really, it's the making of the priority list which is unique to each of the different algorithms. So obviously for, at the start, we just did alphabetical, which really wasn't all that effective. Then we tried to do decreasing time algorithm, which worked, but I wouldn't say was super effective. And now we've got this critical path algorithm, which seems like might be pretty useful. And it turns out once you've done all of that work and you've filled out step three, you actually get a pretty good schedule. The finishing time here is 36 hours. Remember, the optimal was 34, so we're not quite there just yet. Or not actually 34, but 35 as our optimal. Our critical path was 34. That would have been the quickest you could have possibly done it in. But 35 is our optimal. So, I mean, when you think about it, we really were only an hour off of our optimal time. I'd say that's pretty darn good. So again, and here's the schedule, by the way, in case you wanted to take a look at it once you've kind of gone through everything else. So just like we saw in Chapter 6 with traveling salesman problems and Chapter 7 with network problems, we have these efficient algorithms which are also approximate, meaning that they are not optimal, but they're the best we have. There is no efficient algorithm that's also optimal that we currently know of. So at this point, that's kind of the best that we've got. All right, guys, so that's it. That wraps things up for Chapter 8. Hopefully you found everything in this chapter interesting. Obviously, if you guys have any questions, feel free to let me know. Otherwise, have a great rest of your day.